Okay, I'm going to jump now all the way to 4.1. I think it just builds good off of what we were looking at. 4.1 has to do with inverse functions. And for functions to be inverses of each other, there's a couple properties that need to exist. So when we first established what a function was, we said that for every member in the domain, it corresponds to exactly one member in the range. And that looked something like this. So we said, remember we were able to do a mapping. Let's say, for example, A, B, C. As long as each one went to only one, that still was a function. Even though these two were going to the same one, the whole point is that it's only going to one, so that this would still be considered a function. But what wasn't a function was when you had one x going to two different y's. This was not a function. But now we're going to extend the definition. And what I mean by that is that every member in the domain corresponds to exactly one member in the range. And we're going to say that in the other direction. That every member in the range has to correspond to exactly only one member in the domain. So what that ends up doing is that's sort of what the definition of we're going to look at, which is called a one-to-one function. Before we can get into talking about inverses, that's an important idea. We first need to be able to establish what a one-to-one function is. And it sort of says it how it's here, that one corresponds to only one, and that one only corresponds to the exact same one. So in this scenario, so if I did that same thing again, let's say 1, 2, 3, and then 1, 2. So in this scenario, this is considered a function, but it is not a one-to-one function because this y here, whoops, sorry about that. This y is corresponding to two different x's, and that will not be a one-to-one function. It's still a function, but it's not a one-to-one function. One-to-one functions is where you have literally one member in the domain corresponds to only one y, and that one y corresponds to that same x. It doesn't, everything goes 1 to 1. You don't have 1 going to 2 or 2 going to 1. That doesn't happen. It literally has to be 1 to 1, hence the 1 to 1 definition. But to be able to see which functions are 1 to 1, instead of looking at every single point, because remember, if we're looking at a graph, for example, let's say we're looking at x squared. Let me do it down here. Let's say I was looking at the function x squared. We already know what that looks like. That's just a parabola. And we knew it was a function because it would pass the vertical line test. And plus I'm giving function notation, so we already know that it's a function. But to determine if it's a one-to-one function, again, you don't want to, there's an infinite amount of points on this graph. Here's 1, 2, 3, there's literally an infinite amount. So you don't want to be checking every scenario if there's 1 to 1. So the same way we have a vertical line test, there's also something called the horizontal line test. That tells us if our horizontal line intersects your graph more than once, that means that it is not, and this is how some people use the notation 1 to 1, just 1-1. And just like the vertical line test, you don't want to make a vertical line where the graph is only, where it's only graphing where it's only intersecting the graph once. You want to see where is it intersecting it more than once. And if that happens just one time, that automatically means it's not a one-to-one function. So I could list the definition out. So let me write it right here. Definition. Again, this checks for a one-to-one function. So we'd say a function is a function defined by y equals f of x. So remember, it's a function notation. Is one-to-one function if no horizontal line that's what I mean, no horizontal line. Again, you want to find the one that will intersect your graph more than once, because if that happens, you know it's not a one-to-one function. No horizontal line intersects the graph more than once. Again, that's the important part. It cannot intersect the graph more than once. But something else to note here is that we are already assuming that we're dealing with a function. So what that means is when you're looking at a graph, you don't start with the horizontal line test, because the horizontal line test only checks if functions are one-to-one. You first need to know if the equation is even a function to begin with before you even do the horizontal line test. Because it's possible that you might get an example that looks like it passes the horizontal line test, but it wasn't a function to begin with, so you shouldn't even have been trying to use a horizontal line test. And a perfect example of that, so here, let's do an example. We're going to verify. Of course, there's different ways to verify one-to-one, but we're going to use the horizontal line test to do that, to save some time. So, one example is the horizontal line. And yes, if you try making a lot of horizontal lines, you're only ever going to intersect this graph more than once. But I don't want to do the horizontal line test. I want to make sure that I'm dealing with a function. So if I do the vertical line test, and automatically I know I'm intersecting this graph an infinite amount of times vertically. Hence, this is not a function. If it's not a function, then you can't, so it's not fun, I'll put fun dot. So you can't begin to try to do the horizontal line test if it's not even a function to begin with. So it's just something to keep in mind. But let's look at a couple more examples. So 2. Let's look at the functions we've already seen. So the parabola was one of them. We know it's a function because it passes a vertical line test, but it's not one-to-one because it fails the horizontal line test. Some of the other functions we were looking at that we already know are functions would be absolute value. We've also looked at square roots. We looked at cubes. And of course, these we already know pass the vertical line test. All 3 of these pass the vertical line test. Just one because we did it already, so we know this is true. But now I have to see if it passes the horizontal line test. And right away I notice I intersect this graph more than once. So this is definitely not one-to-one. Again, don't make the horizontal line right where it doesn't actually cross. Since I know this is a function, again, horizontal line test. This is one-to-one because it only ever intersects the graph more than once. Because the square root gradually keeps growing, never actually becomes a straight horizontal line. And then this one again, I see all these horizontal lines only intersect this once, meaning that this is a one-to-one function. Again, if you look at the books, there are other ways to verify if a function is one-to-one. But I think using the horizontal line test does save some time. Alright, now we're going to look at the definition of inverses. Alright, we needed to talk about what a one-to-one function is because there's another definition that we need, and it says that f is a one-to-one function if and only if f has an inverse. So the important part here is this if and only if. So that's in math they call it a biconditional statement. What that means is that for one of them, it works in both directions. So what this is saying is if f is a one-to-one function, that means f has an inverse. And then it works in the other direction. If f has an inverse, then that means it's one-to-one function. So these two things go hand in hand with each other. The moment you know that f is a one-to-one function, you automatically know it has an inverse. If you know it has an inverse, you automatically know it's a one-to-one function. So it's not, one doesn't have to come before the other. As long as you know one of them, you automatically know the other one as well. And that's what the if and only if statement tells you, that they both, as long as one of them is true, the other one will automatically be true as well. So that's important because if we know the function is one-to-one, that means that we can find that it has an inverse. But before we get into actually trying to find that, we use the horizontal line test to determine if it's a one-to-one function. But there's also a way to determine if two functions are inverses of each other. So as long as if we both know two functions, so let's say we let both g and f be one-to-one. So that means we know they both have an inverse. But you want to see if they're inverses of each other. So we let g and f be one-to-one for g and f to be inverses. The following conditions are both true. And what those conditions are, they use composition, what we did in the previous video, which you have to check in both directions. So you have to forget f, compose it with g, and once it simplifies, you want to make sure it simplifies to x. And then you have to do it in the other direction, g compose with f, and it has to simplify to x. And this is just to verify if two functions are inverses of each other. Again, if it's a one-to-one function, we know it has an inverse. But let's say when we get into actually trying to find the inverses, this is how you can verify if you did it correctly. Because if it doesn't simplify, so if you compose them in both directions and they don't simplify, then that means, if they don't simplify to x, that means they're not inverses of each other. That doesn't mean they don't have an inverse. They're just not inverses of each other. So here, let's verify. Let's do a couple examples to verify inverses. So example, we're going to verify inverses. So for starters, we're going to have f of x is equal to, just double check you guys can see that, 100 plus 12x, and g of x is x minus 100 over 12. Alright, if you notice, both of these are linear functions. If you remember, like y equals mx plus b. And this same thing is just in a fraction, but this is still a linear function nonetheless. That if we know that we already know they're functions. So that means we're not dealing with a vertical line, because we saw the vertical line, even though it is linear, but it's not a function because it fails the vertical line test. But any other line, for example, let's say, we say we had any other line here, this we already know is a function because it passes the vertical line test and it'll pass the horizontal line test. So we know not only are they functions, but they are one-to-one functions. Since they're both linear, we know they're both going to be one-to-one functions. The only ones that are not a one-to-one function is when we're dealing with a horizontal line. Because even though horizontal lines, that's when y is equal to a constant, is a function, but when you make the horizontal line on the horizontal line, it intersects it an infinite amount of times, meaning it cannot have an inverse. But anything else, remember, whenever you have a horizontal line, that's when your function is just equal to a constant, which that's not happening here. So it either looks like this, or has a negative slope, or has a positive slope. So, but now to just verify these two things. So let me just make a line here, make room. Okay. So to verify the first one, we need to do f of g of x, which, if you remember, that just means we're going to plug g of x into f of x. So if I look now, I know that I know what g of x is equal to, and that's this x minus 12. So if you guys remember composition, I have to replace my g of x with this x minus 12, sorry, x minus 100 all over 12. And then I have to plug in this x minus 100 over 12, into f, which I know f is 100 plus 12x. So that's going to be 100 plus 12. But then wherever there was an x, I'm using my parentheses and I plug in this x minus 100 all over 12. Remember, the goal is I'm trying to simplify. I'm hoping that it can simplify just to x. So right now I know these two 12s will simplify each other, leaving me with 100 plus, I'm left with x minus 100. And what do you know? These cancel and you're left with exactly x. And again, you're not done yet, but that is something that we wanted. We wanted to end up with x. So check, we did that. But now we have to now we have to do it in the other direction. So that's g of f of x. So that means now we're taking we're taking f of x and plugging it into to g of x. That's going to look like this. It's going to be g, And then inside of here is f of x, which we know f of x is 100 plus 12x. We'll move down here. So I know g of x is x minus 100 over all over 12. And again, I'm always putting parentheses where the x was because I'm replacing all of it with this 100 plus 12x. And if you notice here, the parentheses aren't doing much. So you can remove those parentheses and be left with just 100 plus 12x minus 100 still all over 12. And if you notice, the hundreds cancel right away. And then I'm left with 12x over 12. And the 12 simplify, leave me with x, which is exactly what I wanted. So I was able to get x in both directions, meaning that f and g are inverses of each other. Again, we already knew that they were one-to-one functions because we know they're linear, and any linear equation minus the vertical line because the vertical line is not a function, and minus the horizontal line because even though the horizontal line is a function, it would fail the horizontal line test, where everything else will pass the horizontal line test, meaning they would be one-to-one functions. Here, we'll do another example. Again, this is just verifying if functions are one-to-one. So here's another example. Let's say we have h of x is equal to the cube root of x minus 1. And then I have k equal to negative 1 plus x cubed. So again, I have to check in both directions. So the first direction I'm going to do is f, or I guess in this case, it's h of k of x, which just means h, you're going to plug in k of x into h. That's what this is telling us. And we know k of x is negative 1 plus x cubed. And now wherever I have my x for h, I'm going to replace this with negative 1 plus x cubed. So I know h is 3 cube root of x minus 1. And remember, I'm replacing that x with k of x, which is negative 1 plus x cubed. And since these parentheses aren't doing anything, this will become the cube root of negative 1 plus x cubed minus 1, which the negatives end up simplifying to cube root of negative 2 plus x cubed. And then there's nothing else I can do here, because if one of these was positive, that would have been perfect. It would have canceled out and I probably would have had something to work with. But the fact that this did not simplify, it did not simplify to x, that means, again, it has to work in both directions. So the moment it doesn't work in one direction, you automatically know it's not one-to-one. Where here, I guess I didn't say it, but is one-to-one. So that's the nice thing, is you don't have to check the other direction now, because we checked one direction and it didn't work. As soon as it doesn't work for one direction, you automatically know that it's not going to work for the other. I mean, you automatically know they're not going to be inverses of each other, because that's to work both ways. So that's the nice thing that it can help us verify if two functions are inverses of each other. But again, if they're one-to-one functions, you know they have an inverse. And that's sort of the tricky thing of the next part. So we know how to check if something is a one-to-one function. And we know how to check if two functions are inverses of each other. Now, let's talk about how you can actually find an inverse of a function. Finding the inverse. The nice thing about finding, there is sort of a step-by-step process to be able to find it. So something without being said, so this wouldn't be step 1. I would probably say this is like step 0. And what that step is you want to make sure you verify one-to-one. Because if it's not a one-to-one function, remember that definition. If it's a one-to-one function, that means it has an inverse. So you shouldn't be trying to find an inverse if it's not even a one-to-one. So, but once you know it's one-to-one, then you can continue. And what we're going to do is you replace f of x, so because everything's in function notation, by y. So I'm just going to take my f of x, because remember, we know y is equal to f of x, so we're sort of going back to the equation notation that we were using before. And then once you replace it, you're going to interchange x and y. What does that mean? Is that wherever you see an x, you're going to change that to a y. Wherever you see a y, you're going to change that one to an x. And then once you do that, you're going to solve for y. So try to get y isolated. And there's a couple tricks that on some of the examples, if there's a nice trick to do to be able to find the inverse. And then lastly, you're going to now replace y by f inverse of x. So this, I didn't write it earlier, but this is inverse notation here. That -1, be careful. That doesn't mean a negative exponent where you can rewrite as a fraction. That's just the notation of an inverse. So if you see that -1 as an exponent next to function notation, it's not implying to rewrite it as a fraction. That is telling you that that's an inverse. And then you can verify. So again, it's if you verify it as one-to-one. So this isn't necessarily step 5, but I'll put 5. And you can verify. This is the part where I'm saying that you can check your own work to see if you did it correctly. You can verify inverses. And again, it's that same note, but what you want to do is plug them in both directions and hoping that you get x. That it simplifies to x in both directions. And if you see now, what I'm doing is I'm using the inverse notation, that -1. So don't get confused. All it is switching the notation up a little bit. It means the same as this definition that we looked at earlier. These two mean the same thing. Instead of just saying f and g, we're saying f and f inverse. Because we're assuming that we did all this work and we found the inverse of the function. So that's why we're using that notation. But then we're verifying it to see if they are inverses of each other. Because maybe we made a small mistake and dropped a negative and thought they were inverses of each other, but they weren't. So let's do an example. We'll start with something small, nothing too crazy. So we're going to find inverses now. So for starters, we're going to do, let's say we have f of x is equal to 3x minus 1. Alright, so again, this is a linear function. How do linear functions look? I can draw, again, this has a positive slope, so I know it's going to look something like this. Again, it's a parent graph. We know the slope is positive, the y-intercept is -1. So I know it's going to have this positive slope, which I know this is definitely a one-to-one function. Because it'll pass, we know it's a function, you know it passes a vertical line test already, because we're already writing it as a function. But even so, you can think about the graph, and you know this graph will pass the vertical line test, and it passes the horizontal. So I know for sure it's a one-to-one function. What I want to verify now, what I want to do now is actually find the inverse of the function. So to do that, like I said, the first step is replace f of x with y. So we're going to write y. So that was step 0. This is step 1. I'm going to replace my f of x with y. So that's y equals 3x minus 1. Now maybe this reminds you of y equals mx plus b. Second thing is interchange x and y. So that means this y is going to become an x, and that x is going to become a y. Now step 3 is isolating this y. So to do that, I need to add 1 to both sides. The 1's cancel here. I'm left with x plus 1 equal to 3y. And then to get y completely by itself, I need to divide both sides by 3. Leaving me with x plus 1 over 3 equal to y. So in all these steps, in all this work here, we're essentially doing step 3, which was solve for y. Now that we have y isolated, all I have to do now is take y and replace it with f inverse of x equal to x plus 1 all over 3. And then for the sake of time, I'm not going to verify it, but you should verify that. So try doing that. So you're going to take this and plug it into here. And then vice versa, you're going to take this and then plug it into this side. So try it, see if you get that they're inverses of each other, if we did it correctly. If not, let's do another example. So these next ones are usually the ones that cause students the most trouble. So let me box this off. So next example, we have f of x is equal to 3 minus x over x plus 3. Alright, we haven't graphed these types of functions yet, but they're considered rational functions. And for now, I'll tell you that this is a one-to-one function. We know, so that's step 0. We know this is a one-to-one function. And in later videos during the week, you'll see why it is a one-to-one function, but that's when we get into talking about graphing rational functions, which I skipped really quick just so we can talk about inverses and a couple other functions. So Here we go. Let's verify this. So first thing I'm going to do is I'm going to replace that f of x with y. And I'm left with 3 minus x over x plus 3. And then step 2. So I'm going to bring it up. I don't know why I did all that, but it's up here. Step 2 is now everywhere I see an y, I'm going to replace it with an x. And everywhere I see an x, I'm going to replace it with a y. And now the third step is being able to solve for y. So this is the one that usually gives most people issues. But what we have to do, if we're going to solve for y, we need to try to get it out of this denominator. So to do that, we're going to multiply y plus 3 to both sides. So again, I'm trying to squeeze in here. I'm going to multiply y plus 3. And then same thing on this side. What that does is now I have y plus 3 equals 3 minus y. Because when I multiply this y plus 3 on this side, it's going to simplify that denominator. Oops, I forgot there's an x right here. I should just put it on this side. X. So, again, the tricky part is I want to solve for y. But now, instead of being in the denominator, it's in parentheses now. So hopefully what you're thinking is, let me just distribute. Which that would work. You get x, y plus 3x equal to 3 minus 1. And our goal, I know it seems tricky because this x, we have two y's now, and this y is negative, and then this y is stuck with this x. But again, I would still keep going. I'll still keep trying to just isolate the y. So to isolate it, I need both y's on both sides, on the same side. Even though this has an x, I still want it on the same side as this other y. So again, it's up to you how you want to move things. But what I'm going to do is I'm going to add y over to the left-hand side. And then on the right-hand side, the y is going to cancel and be left with x, y plus 3x equals 3. So to continue isolating, at least now I have them on the same side. But this has no y's in it whatsoever. So I'm going to subtract that one to both sides. Cancels on the left-hand side. And then I'm left with x, y plus y equal to 3 minus 3x. And this is where the trick happens. Is that I know both of these two terms have the same variable. Have the same factor. And hopefully you remember at the beginning of the semester, we always said there was something you should always do first, and that was factoring out the GCF. So if I factor out y, I'm left with x plus 1, 3 minus 3x. Now all I have to divide is both sides by x plus 1. And now, so all this work was step 3. Now step 4, all I have to do is replace this y. Just for the sake of space, I have to replace it with the inverse of x, leaving me with 3 minus 3x all over x plus 1. So, I'll try to post more examples of these on our Instagram page for this week. But for now, that's all I want to cover. There are other problems we're going to look at, but I'd rather not do those now. But let me give you some homework so you guys can practice some of these problems. And I'll post the test soon as well. This will be our last one for the semester. And if you're asking yourself, we're supposed to take 4. What I'm going to do, I'm just going to drop that test and then use the other 3 to sum up your grade. And I'll do it in such a way that it benefits you as best as possible. So it gives you the best grade possible. I know things didn't work out perfectly, but I'll still try to make sure everything works out. So let me give you some homework. This is from 4.1. Please keep a lookout. I'm going to be posting more problems later, more videos later today about 4.2 and 4.4. I'm going to try to put some of those ideas together. 4.2, 4.3. And then I'm going to teach, go back to chapter 3, do a couple of things, and that should be it after that. And then, but I'll keep you posted. So here's some problems. So from 4.1, let's try 13. 13 is good. Let's do 16, 17, 21 and 22. Hold on. Let's just do 21. Now, what we did is being able to determine if 2 functions are inverses of each other. So try 31, 33. That should be enough. You can try 35 if you wanted an extra problem. But now, last one is actually try to find the inverse of a function. So that'll be 41. Let's try 41 is good. Try 40. I'll put 42, and 43 is a little tricky. If you need help, please come to my office hours. I can help you with that. We'll do 46. And we'll do 49. And I think that's good for now. I'll leave it there. So try doing these. It's not too many. If you have any questions, please let me know or email me. And on that, thank you.